Hello and a very warm welcome back to my channel. Trust you're all well and in good spirits. Just a quick response to a comment on the Facebook teacher chemistry page about how to use WebMO to calculate the Debye units or the dipole electronegativity in a given molecule. So what I suggest you do is you go into WebMO, the logon as usual is guest. I'll just show you that very quickly if you've not done this before. This is a free to use program. Click on there, guest, password, guest, okay. Click onto that, and as you go in, you will drop into this area. Go to the top left, new job, create new job, click that one. This is the landing screen. This is the first screen that we come to. The buttons on the left hand side, the main ones are this one, the periodic table. This one allows you to clearly to rotate, to zoom in, to translate, to adjust, choose, all these things. It defaults to carbon, so I can click, make carbon drop, click another carbon, click and drop, and I will form one bond in between those two atoms. Be very careful that you, let's take the mask off. Be very careful that you don't put another carbon atom in behind it, so you have to very carefully drag from the middle of this atom to the middle of this atom, but I'm sure you will get used to it. I want to add some electronegativity, so let's just choose chlorine. I'm going to add a chlorine atom here. Nice big juicy chlorine atom, and beautifully coloured in on the bonds, going from black to green. It's not a very good chloroethane, is it? So what we're going to do, you can clean up, you can add hydrogens, that's good, we've added the hydrogens. You can add the spinning tool and you can have a look at this, which is quite nice. What's very important to do on all of these is a comprehensive cleanup, idealized or mechanics. I've been going with idealized recently, and look at that carbon-chlorine bond length, it's just zoomed out there. We can look at the molecule, clearly if we hit this tool, we can spin it around. We can see it in 3 dimensions, which is great as a teaching tool. We can look into here, we can look at the electrostatic potential. So if you're talking about the nature of the electron or whereabouts it's distributed in a molecule, you can remove the molecule, take the molecule out, and spin this around in space, which is perhaps closer to reality. Look at the electron density on the chlorine substituents there. You can also look at the electrostatic potential. We've already done that one. And we can also look at the strain energy. The strain energy is pretty useful. Total energy of the molecule here in kilocalories per mole. You can easily change that into kilojoules per mole. You can look at different substituents, you can do the halogens, you can put different functional groups on, and there's no restriction that I've found on this front screen in terms of the complexity of the molecule and the results that you get. So clearly this is the total energy, which is summed up by the bond stretching, angle bend, stretch bend, van der Waals radius, and electrostatic interaction. So perhaps you can have a look at that. But let's go back to our original molecule. Is there anything else that we can do on here? Not really. I think we're pretty good. So we've cleaned up, idealized, spun it around. We can look in databases. I've shown you this on a previous video. I'm not going to do this now. We're going to look up the NMR or the IR or whatever it happens to be on here. But the question was in particular in relation to the dipole moment in this molecule. So for this, we need to go down here to the bottom of the screen, hit continue. We're going to use GAMES at the top. GAMES is the engine that we're going to be using. We then drop into this screen. The job name is my chloroethane. We're going to be doing molecular energy. We want the molecular energy. Clearly, other options down here you can also do. Molecular orbitals is perhaps a bit beyond IB. We can generate all of these, have a play with it. Theory, going to be using UHF, and we want accurate. So UHF and accurate. Don't change anything else that's in here. And then click the forward arrow. Once you've clicked that, your job will be submitted. You can see I've done this previously just to prepare that it was going to work. There is a limit on the complexity that you can do in here, but it seems like monosubstituted alkanes are playing quite nicely in a total time of 4.5 seconds. I click on my molecule, and then what happens is it should pop up here. Nothing looks particularly different from the previous image that I showed you. You've still got your ability to spin the molecule around. You can still calculate the strain energy in the molecular orbitals. You can look it up on the databases, which is great. You can clean it up. We've already done that. Don't forget to do that at the beginning. So what's different? Well, if you go down here, you can see that we have the UHF. This is the energy of the molecules in Hartree units. I've mentioned this before, but Hartree to kilojoules per mole, the conversion factor is 2625.5 kilojoules. So you can easily pop that into IB language from Hartree units to kilojoules per mole. The question that I'm answering was what's the dipole moment in Debye units? Here it is, 2.240083 Debye units for the dipole moments. You can also click on the molecule. Click it once, you get the hybridization. Click it twice, make sure you click the right one, Mr. Midgley. There we go, we get the bond length. Click it 3 times, we get the bond angle. Click it 4 times, you get the dihedral angle, but that's not the subject of this video. The question was, how do I get the dipole moment? There is your answer. Okay, hope you found that useful. Keep playing with WebMO, keep subscribing, keep smiling. We'll get through this. Thanks very much for listening. See you later. Bye.